Here we see how Einstein reduces his general relativity theory to Newton's theory in the limit where Newtonian mechanics should hold. Let's consider the geodetic equation, and let's rewrite it like this: d squared x tau with respect to ds squared equal to gamma tau mu nu dx mu ds dx nu ds. This is the geodetic equation written according to Einstein's convention. In other books, as I have said multiple times in the previous videos, you see this gamma symbol with a minus sign, but according to how we have defined this gamma symbol, and if you go back and check other videos, you will notice this, you will find that gamma here is written with a different sign. But anyway, for a system in which gravitational effects can be neglected, G mu nu is approximately equal to this matrix minus 1, minus 1, minus 1, 1, and then we have all zeros out of the diagonal like this. And as I have said in previous videos, the time dimension according to Einstein's convention is the 4-4 element here. We will consider a small deviation from the special relativity case, and also since velocities in this case are much smaller than the speed of light, we have, and let me write it here, that d squared x tau with respect to s squared is approximately equal to gamma tau 4 dx4 ds dx4 ds. Why is this? Well, because as I said, velocities in the special relativity case are much smaller than the speed of light, and therefore we have to consider the differentials with respect to the time coordinate. dx4 is the differential of the coordinate related to time, and in special relativity dx4 over ds is approximately equal to 1. This is approximately 1, and this is also approximately equal to 1. Whereas the other derivatives, dx3 over ds, dx2 over ds, dx1 over ds, are negligible and much smaller than this derivative here, dx4 over ds. So they are much smaller than 1. And this is equal to minus a symbol that we have defined previously, curly bracket 4 tau, and Einstein uses this symbol. And in books, this is what is usually called gamma, the Christoffel symbol, gamma tau 4. But according to Einstein's convention, this is minus gamma. So that's why we get a minus sign here, because gamma tau 4 as defined by Einstein is minus curly bracket 4 tau. And this is also equal to minus square bracket. Einstein also defines the square brackets 4 alpha multiplied by g alpha tau. And this tensor equation leads to these four equations. We have d squared x tau ds squared approximately equal to, or just equal to, let's write an equal sign here instead of an approximation symbol, square bracket 4 tau, where tau in this case can be 1, 2, or 3. And we also have the fourth equation, d squared x4 ds squared equal to minus square bracket 4. This minus sign here comes from this metric tensor right here. And here we have a plus, always because of this. Now, let's rewrite this equation here. D squared x tau with respect to s squared is equal to let's substitute for the definition of the square bracket. This is 1/2. Then we have the derivative of g for tau with respect to x4 plus derivative of g for tau with respect to x4. They're the same term. These two are equal. Then we have minus dg for 4 with respect to x tau. Now we will neglect these two terms by assuming that the field is quasi-static. Why can I do that? Well, because this term can be written as 1 over c dg for tau with respect to dt, and we will assume that the speed of light that appears in the denominator here is much larger than the derivative of this field. So the field should not change so rapidly that this ratio here, this 1 divided by c, will be non-negligible. So it must be negligible. This 1 here can be neglected, and we will assume it to be almost 0. So from here we get d squared x tau with respect to s squared equal to minus 1/2 dg for 4 with respect to x tau, and remember that in this case tau should be 1, 2, or 3. And now also remember that we have these equations, the field equations that we derived in previous videos, d gamma alpha mu nu with respect to x alpha plus gamma alpha mu beta times gamma beta mu alpha equal to minus k times t mu nu minus 1/2 g mu nu times t. And remember that we use this equation in conjunction with the fact that the square root of minus g should be equal to 1. The only non-negligible term in the energy tensor in this case is T44, which is rho c squared, and of course this is the term that is non-negligible because of the presence of c squared, and this is also approximately equal to t, and remember that t is defined as t mu mu, like this. Also, this term here is a quantity of second order that we can neglect, so we are left with only this equation, d gamma alpha for 4 with respect to x alpha equal to minus k over 2 rho c squared, and we can rewrite this term on the left. This is equal to minus d over dx alpha square bracket 4 tau g alpha tau, and this can be written as d over dx1 of 4 square brackets plus d over dx2 square brackets 4 plus d over dx3 square brackets 4 and finally here we have minus d over dx4 square brackets 4 like this. Let me close the bracket, and these three terms, if we put these three terms together with the approximations considered, they are simply equal to minus 1/2 del squared, so the Laplacian of g44, whereas this term here will be negligible according to what we have said earlier. We have the derivative with respect to time there. Therefore, we have found these equations, del squared g44 equal to k rho c squared, and we also have these equations that we found earlier, this one here. So let me rewrite it below. we can rewrite that as 1 over c squared d squared x tau dt squared, simply because ds squared is c squared dt squared. Remember that we are in a special relativity case, or approximately in the special relativity case, and this is equal to minus 1/2 dg44 with respect to x tau. And in this case, tau is either 1, 2, or 3. According to Newton, we can write these equations, Newtonian physics, in this manner. We have the Laplacian of a scalar field phi, which is equal to 4 pi g rho, and we also have the equation d squared x tau, where tau can be either 1, 2, or 3, dt squared equal to minus the gradient of the field phi, d phi over dx tau. If we compare these two pairs of equations, if we choose g44 equal to approximately equal to 1 plus 2 phi over c squared, so this one here represents a small correction to the metric tensor, to the 4 component of the metric tensor, and we also consider k equal to 8 pi g over c to the fourth. And if we substitute these two expressions here, you can easily check that you will find Newtonian physics. So you will find these Newtonian equations. And these are Einstein's considerations that show how his general relativity theory reduces to Newtonian mechanics. In the special case, of course, where its laws should be applicable.